Anyways, we'll get started in a couple minutes, but to save enough time so that we can do discussion, maybe it's better to talk about the administrative parts first. Hi, Samson.
Hello.
So this is our reading group that we have at NUS. So we are a research group here at NUS doing natural language processing type. And we, as a group, decided that we were going to have presentations and discussion on papers that are in natural language processing interest to probably a wider audience. And this is why we opened it up. So those of you who are external participants, can you introduce yourselves for a minute? So do you want to start, Saravana?
Yes, I'm Saravana, currently working in A-Star High School. I'm a part of Semantic Analytics Lab, and most of my previous assignments were building NLP models.
NLP models. Okay, welcome.
Hi, I'm an undergrad in NUS. Right now doing my final year thesis on applying news to stock market tradings. Right now I'm currently working part-time in Shopee as well. And a lot of my work is also NLP related.
And your name is?
My name is Karkin.
Karkin.
Just call me KK.
Okay, KK. And yourself?
I'm a first year PhD student, EAT, my name is. I'm under Prof. Wong Wenpa, working on high performance computing and deep learning. More specifically, my research will be focused on spiking neural networks and its hardware implementations, stuff like that.
So Yugit was actually part of our 6101 from last semester and couldn't make it, so he's participating on our reading this semester. And yourself?
I'm Shavia. I'm a second year PhD student under Prof. Mehul Mekhani from the ECE department.
Or ECE?
Yeah, and my research is more of the theory of deep learning, like trying to understand why it's able to generalize well.
Okay, and we have a couple of people online, so I'm going to ask you guys to try to introduce yourselves. So I see there's Justine. Do you want to just say a couple words about yourself? I don't know whether we can hear you. Let's see. So any one of you who are online, can you say anything to see whether we can hear you? I'm worried that the speaker is not.
Hi, are you able to hear me?
I don't think anything's working. Let me see.
Hi, can you hear me? Hi, can you hear me?
Can any one of you say something?
Hi, Prof. Can you hear me?
No, okay. I don't know why there's no sound. No, I'm just a laptop. Hello?
Hello, Prof. Can you hear me?
Okay, since I don't know why, we're not going to troubleshoot now.
Hello.
You're talking, but we can't hear a thing. Okay, let's see. And let's see whether Zoom is. Hope we can connect to something else.
Hello.
Audio. Let's see what
It's trying to play through the microphone.
It's trying to click that way.
Oh.
Hello?
Hello.
Okay, now it's working. Great. So we'll try to put it to the external mic. External. Let's see whether that works. Okay, seems to work. Okay, so maybe we can start with those of you who are on remote. So I'm going to skip our own wing members and then ask the people who are online, not from our group, to introduce themselves. So Justine, do you want to introduce yourself and what you do? Justine, can you hear us?
I think Justin is not there.
Okay. Nam, do you want to introduce yourself?
Yeah, sure. So I'm currently working at a property guru, and I'm just in general curious about this field in NLP and deep learning.
Okay, great. Then let's see who else is online. So Taka, do you want to introduce yourself?
Yes, Prof. Can you hear me? Hello?
Yeah, we can hear you.
Okay, yeah, great. My name is Taka. Currently, I'm working at Fook, which is a startup doing something like Netflix does. So I'm working as a data scientist and also working some recommendation engine under some information retrieval stuff. So I'd like to expand my skill and knowledge by participating this reading group. That's why I'm participating. I'm here, and I also participated a couple of sessions CS6101 before. So yeah, I'm looking forward to studying new things from this opportunity.
Great.
Thanks.
Yes. So Taka has been with us for quite a number of iterations. So thanks for joining us again. Chin Hui, can we ask you to introduce yourself? Maybe they said that you never know who's actually in front of their computer when they're online, right? That's one problem. So thanks for joining all of you to join us in place. So I'm just going to give a couple minutes of administration for how this will run. I'm not going to battle to switch screens. So Wing NUS is one of our research groups here. It's led by myself. We have about 5 PhD students, 5 undergraduates, and almost 5, I think 4 master students right now. And as I introduced earlier, our group decided that we were going to have a reading group, and I mandated it to be public. So PhD students are required to do 2 lecturing slots. That means the class is divided into 2 halves, one before week 7, which is the week after research week, recess week in NUS, and then 8 through 13. So all of our PhD students have to select 2 lecturing slots. So you're responsible for helping out for 2 separate lectures and 1 scribing slot. And so I'll overview what that means. Okay, everyone else, that means undergraduates participating from my group, as well as external participants who are online, as well as here, you guys are responsible for being lecturing and supporting 1 time each. Okay, and so I need this commitment from you. If you're interested in looking through the materials and then watching the presentation, you can do it on YouTube. We'll put up the information later. But then I won't ask you to participate in Zoom. So if you want to have a more interactive, then you have to commit and help out. Okay, that's the only way this works. Otherwise, it's getting lecture for free, which unfortunately we don't do. Okay. So how this works for us is that you can think of this as 2 different responsibilities. Okay, this has been refined over about 5 iterations of things like this. Okay, which means that we have a group of presenters whose job it is to look through materials from online sources and compile some slides. And of course, they're not going to be as nice or as refined as people who do this for a living or spent a lot of time doing tutorials, but that's not the aim. Okay, this is a reading group. So it means they're just to facilitate. Okay, It's completely fine to ask dumb questions, and that's the whole point, is to get everyone's level up a little bit more. People who already know the subject well will benefit from the having to teach it or clarify doubts for other people. Okay, people who don't know the subject material well will of course learn it. Okay, so the lecturing slot is more like the preparation, right? Like how to get things ready. So the lecturing staff will present slides, but they don't have to be clear about everything. So you just shouldn't think of it as, you know, you have to actually lecture like a lecturer does. Okay, to facilitate thought, to find materials and say, you know, okay, these are some slides. I watched this video or something. This might be helpful. Okay, and then there's another class of role that again everyone has to do at least once. Well, once. Okay, which means that a supporting staff member, somebody assigned to that role, will have to complement the lecturing staff. So you can think about it this way. This one is more like before the reading group, you have to do some preparation. Okay, and this one is more for during the reading process. Reading group process as well as post reading group, we would like you to contribute, okay? Because you guys all know there's plenty of material online for NLP or deep learning in general. We benefit a lot from things outside of just archive papers, so we should try to contribute back, okay? That's all. That's all it means. It doesn't have to be professional. It just means we make an honest effort to do so, okay? So the timeline for how this works is that unlike this week, because it was the first week, okay, hopefully by Monday, the next group for week 5 will have a paper list ready so that we can disseminate it by Slack. Everyone can either download it or print it on hard copy, whatever, so that everyone in the group can actually do the reading beforehand. I apologize we didn't get our act quite together for this round because I was busy with things. Okay, then there will be the actual reading group. Okay, then by Monday, the YouTube video of the lecture will be clipped properly by the support staff or by our meetings manager, Taha, who's sitting here. He's the one in my group in charge of all of our meetings. So we will try to clip the video properly and annotate it with a description. Okay, and then by Friday, meaning the next reading group, the scribes for the week before have to finish their duties. Okay, so that makes it you know, pretty close knit. You have basically plus or minus 1 week window to get everything done for 1 week. Okay, so this is the commitment that I need from all of you who are attending this, right? I don't. In the past, we've had cases where students said, "Oh, I got busy. I'm sorry I couldn't attend, but I consumed all of your lecture material, and I thank you for all the workshop," and then they say bye-bye. So I want to minimize that as much as possible. I realize that external participants don't always know what happens in their schedule, especially if you're in a professional line of work, and so you may have to call it quits, but as much as possible, I'd like to make sure that you commit. Okay, and for that reason, we have that worksheet that you saw, right? And I hope everyone has visited it. Have all of you gone to the bit.ly link? Okay, so there's a bit.ly link for, let's see, what is it? Okay, which all of you need to fill out. So if your name is not here, please add a row. Okay, you may not be able to edit some parts of the worksheet that are in blue. These are for me to allocate. Okay, but you have to put your name down for here and then tell us, importantly, which weeks you want to lecture for and which weeks you want to support for, one of each. Okay, for our PhD students, sorry, you guys are arrowed for 2. Okay, that's a consequence from being my student. Okay, maybe you want to change supervisor. So anyways, this is the allocation of the current topics that we have, right? So today we're going to go through BERT and transformers. Next week, graph-based models, multimodal models. Then we'll do recommendation systems on week 7. Semantic analysis in week 7. Sorry, this is during recess week. And then the second half, we have applications more like text summarization, i.e. named entity recognition, neural machine translation, machine reading comprehension, looking at dialogue and discourse, for example, chatbots. I think some of you may be interested in that, as well as entity linking. Okay, so my goal is to try to fairly allocate so that we have nobody left alone. Okay, I think that's important. I mean, if you were responsible for an entire reading group session, it may be a little bit onerous. So we don't want to make it onerous. We want to make it interactive. Okay, that's the goal. Okay. So if your name isn't on this worksheet, please access it. The access link is right here. If you have a mobile device, you can add your name right now. So you can just go to row 25 and add your name there. Okay. If you're not sure what to look at, again, the current list of things is on this particular tab. Okay, and then you can look at what weeks are there. All right. So I expect you to have done that. Okay, there's just a little bit of other information that I want to share with you is that we don't have good coverage on some of these topics. So in fact, I think there are a couple people in my group who are thinking of changing the multimodal model lecture to a style transfer model. So if you have an opinion about that, please tell us now. I mean, we're all physically here in the room. Do you guys have an opinion? Would you more prefer to see multimodal models because you're working with multimedia? And if so, would you want to volunteer for that session? Yeah, I'm going to pause until someone starts talking. Otherwise, it's always the lecturer talking. It's not a good thing. Any opinions?
I think multimodal would be better because nowadays we are dealing with multiple file formats. So multimodal.
Multimodal. Okay, I vote for multimodal.
It's too broad.
Too broad, so we have to narrow it down a little bit. Maybe something like image to text or something like that. Something of this sort, like captioning methods or something like that. So please air your views if you. I mean, this is a reading group; it's a discussion group, so I hope everyone will speak up. Don't think it's not fair for you to speak up. So if we wanted to make it more narrow, what would we do? I mean, you also said maybe keep it multimodal, but do you have a specific modality that you're interested in? And would you want to present on that, even though maybe you don't personally know very much about it? I don't know whether it's your research area.
It's not mine. It's comparatively new to me.
Uh-huh. Yeah, let me comment on that. No, we can't hear you. Oh, this was a while ago. Yeah, sorry. Anyone else have a opinion? Nope. Okay. Then I'll make a decision based on what my group needs to get out of it as well. Okay. Any questions before we start about requirements, anything of this sort? Okay, my goal is, again, this is a discussion group, so I hope you guys will all think in your head, okay, I need to talk at least once during these 2 hours, okay, because if not, it's going to be lecture, and then it's going to be too heavy. Yes, sir. Your name?
Gillian.
Gillian.
About the reading, like, how far in advance should share the readings with the rest of the group? Because I think this week I didn't have time to read because I only talked about them.
Yeah. So really good point. So we went over it right before you came in. So this is the timeline. You're supposed to get the paper, let's say you're doing week 5, which is next week, okay? Then by Monday next week, you should have the paper list settled on, at least preliminarily. I mean, like a basic paper in that area, you should circulate early, okay? Like there could be extended, like incremental work that's been done since then, or recent work that you want to review on archive. Then please go ahead and do that, but you may not need to circulate it so early, all right? So at least the basic paper, like for this one, it would be the all attention is all you can need paper and the BERT paper. Those are the 2 basic ones that we expect that you have had a chance to read if we had done our homework and broadcasted on time, okay? Does that answer your question? Yeah. Great. Any other questions? So you've met your quota for today, thank you.
Yeah. I think there was another, the last slide had something about presenting on your research interests. So I was wondering whether there might be interest in a session on argument mining.
Argument mining?
Yeah.
Okay, yeah.
So I'm in with the IBM debater kind of data sets and papers on it.
Okay, yeah, we can do that maybe. So maybe we can put discussion on Slack as well. I mean, our scribes can note it down so that we can remember. Okay, that's why we have scribes, so our presenters don't have to be bothered with that. So argument mining, maybe making the multimodal lecture more specific, something of that sort. What do you guys think about this? Having a sharing session where everyone, especially external speakers, can talk a little bit about their own area of interest. In previous 65101s, we were concentrating on a specific research topic. So for example, deep reinforcement learning, deep unsupervised learning, and you had to do a project in that area. But this time we don't have a project component because it's just a reading group. Wing members, would you like to hear from other people outside of our group? Yes, yes, yes. Okay, so how about you guys as external folks? Any of you online as well as in the room care about this issue? Like, I don't have time, or I really would like to share because I think it's good to network, or what's your opinion? This is argument mining, yeah.
I don't mind doing this sharing on adversarial attacks of NLP. So I'm doing that as a project.
Okay, adversarial attack on NLP. So we have another PhD student sitting two spaces next to you doing exactly that as well. Okay. How about the rest of you?
I think I'll share it later to the topic on RL with respect to question answering.
Reinforcement learning. Okay, so yeah, I mean, you can weave it into your presentation as well, but we can also have one session where we are being more social. I mean, outside of the reading group. Okay, I'm a big fan of social gatherings for academics because I think it really does help improve your research capability when you can communicate your research to others and when you can cross-pollinate your research with other people's interests. Okay, so typically in 6101, last couple of semesters, halfway through the term or at the end of the term, we go out for dinner one night. So we just have a chance to chat. Okay. It's not really a sharing session per se, but it also serves a purpose.
Yeah, maybe I don't mind sharing a bit of like time series data with NLP as well, maybe towards the end of the course when I'm presenting.
Okay, great. Okay, it looks like people are up for that, so I'll try to schedule some time for that. Okay, if you have restrictions on the timing that you think you'd like to have this done, for example, if you're an NUS student, probably week 14 is a really bad week to have this, then we can schedule it earlier. Okay, so if this is really for external participants, how do you want this reading group to run? Like, we don't have projects anymore. So especially Taka, since you were here over the last couple of semesters, do you have any input on that? Taka, are you there? Yeah, it's tricky to yeah, go ahead. Taka, do you have any input on whether you'd like to see projects or some other form of reinforcement of the concepts that we're discussing?
I don't have a specific idea right now.
Okay, so no specific idea. Anyone in the room have any input on that?
Is there any way that we can get like some hands-on experience rather than just reading papers?
Yeah, so this is what we're discussing, whether there's a way that you guys want to see some type of reinforcement of the concepts that you learned from reading the papers. So for example, we could ask everyone to team up with a partner and do a homework assignment that comes from some lecturer in some university on that topic. Right, that might make it easier. You can just go search for a homework assignment and do one of the exercises, right? And then you can make that part of the sharing session at the end of the course.
I think that would be a good idea.
Okay.
Yeah.
Thanks, Nam. Anyone else, either locally or remotely?
We can have some tutorials on administration, and even on BERT. Yeah, and other models like for Grab can have a very quick tutorials on one of the recurrent libraries on the Grab learning.
Okay.
And perhaps running through implementations of several papers.
Okay. So we can do that. For example, if you're a lecturer, you can decide to make it more interactive by giving a demo from some website or some app online that can do that type of learning. I don't think it should be made compulsory though. That's my one thing I don't like about a lot of conference presentations is you spend a lot of time on the results. So unless the results are particularly interesting, we all take it for granted that the paper is, the current best state of the art for that time. So we don't need to present that information. Okay. All right, if there's no other things that we want to go over, then let's spend the next hour or so going through the slides. So today we have Abhinav and Cara going to give the presentation on BERT and transformers. You guys discuss which one of you are going first?
Oh, yeah.
Okay, all right. So you want to use the mouse here, or you want to broadcast from your computer?
I think I can use.
Okay. So you have keyboard and mouse. Yeah. Oops. Not this one. Yeah, it's here. Okay, so we're on the PDF file that was sent in the general channel, I think. Oh, that's the newer one, right? Okay, let me put it here. Okay. Computer. Okay, so let's get started.
Okay. Okay, so today me and Cara will be talking about transformers. So today we are going to talk about what transfer learning is in general, and then we would want to talk about how can we do some kind of a pre-training on text before we can fine tune on other tasks. We'll be talking about transformers and BERT. I will be giving a very brief introduction to attention, where self-attention comes from, how is it used in transformers, and how transformers are used in BERT and pre-training and so on. After that, a very brief introduction to some other variants of BERT, which are being introduced by the day. Lot of transformer models, pre-trained models, which are being used. So let's get started. So what exactly is transfer learning? One thing that we can look at is traditional machine learning. You have different kinds of tasks, and then you would want to learn a model for each of them. That's how traditional machine learning works. But transfer learning takes one different approach, where you have a set of tasks. Between these tasks, there is some knowledge that you can get and use this knowledge on a target task. So you have the source tasks, and then you have the target tasks. So you will apply the knowledge which you learned in the source task to the target task.
So these source tasks require some kind of common knowledge to be learned. Maybe you want to learn some common linguistic representations, which can be useful in the target task as well. Or you would want to, you have some structural similarities which you can learn in the source tasks, and then you can apply them to the target task. So this is the basis for transfer learning. Sometimes the target task is very complementary to the source task. For example, if you are able to answer questions on a paragraph, then maybe you are good at forming questions on the paragraph as well. So there's some kind of supplementary and complementary information. Sometimes you have some kind of a new language or a new task where there is not much annotated data, and it's very hard to annotate data. So you gain knowledge from tasks which have huge amounts of training data, and use the model that you learn on it on the target task. So this is some basis for transfer learning. So this is a taxonomy for different kinds of transfer learning. What are the different kinds of transfer learning you can do? This is from Sebastian Duda's thesis. So you have same tasks, or on the top side of the graph, it talks about same task where the label data is only in the source task. So, but there is no label data on the target task. On the bottom, you have different tasks. So the source task and the source and the target are different tasks, and you have some kind of a label data for target task as well. So this is called as inductive transfer learning, and we'll be seeing what is it. We'll be looking only at inductive transfer learning. And in inductive transfer learning, you either learn the source task and the target task simultaneously, which is called as multitask learning, or you can learn the source task first, build a model, and use that model to learn the target task. So which is called as sequential learning. We'll be looking at sequential transfer learning only today. So anything that you have to anything you have to say till now?
Yeah, so questions, please.
Lot of source and target.
So what types of things would qualify as source and target? Can you give some examples, or you have some?
Yeah, I think it comes next. The source task can be anything like transfer learning, natural language inference, machine translation, and so on. So those are the source tasks. Maybe the target tasks are like question answering and summarization, sentiment analysis, question generation.
How does transfer learning relate to joint learning? For those of you who are on. So here we have two tasks, right? Task A and task B, right? One is a source, one is a target. Okay. So what about joint learning, right? Joint learning means that you learn both A and B at the same time, or something like that, right? So how do these things relate to each other? You don't have to give a right answer. This is not a lecture. Okay?
The multitask is more related to joint learning.
Multitask is more related to joint learning. Yeah. How so? No one say.
Because both here the tasks are learned simultaneously. So joint learning is more similar to, I think joint learning is maybe more similar to multitask learning. I'm not sure.
Yeah, I think you learn two tasks simultaneously. Like I said, question generation and question answering, maybe, where one task helps the other. So you would want to learn some kind of a common representation between the tasks, which will help both. And sometimes it will even help you generalize because you're getting more information from the other task. Yeah.
So for multitask learning, are there a set of weights shared between the two?
Yes.
So it's
Yeah.
like two different models sharing the same weights, and like
Until some level.
outputs
Yeah.
of different tasks.
Yeah. Yeah. I think yeah.
I'd like to clarify something. So for transfer learning, usually what is transferred from the source task to like the target task, right? In terms of embedding. So we kind of train some like algorithms and use the same ingredients on like the target task.
Yeah.
Or is there any other way?
So the question is, here you are learning some kind of representation like word vectors, and you are transferring it to some other task. Is there any other way to do it?
Yeah, as in like word embeddings is one way, right?
Yeah.
Of this transfer learning, is there any other types of transfer learning? What is being transferred within like the target? So from the source and the target.
Usually the representations, but if anyone else has an answer, then
You guys all know what we mean by representation. Can anyone define it for us?
So how we transfer the text sequences into representations that can be computed on, like for example, the words can be represented by the vectors for each word, or two vectors for each word, fall into that, or whether you can represent a sentence as a vector, for example. So that's one approach. Or the other approach would be like count-based approaches, where you just have a vector with a number of counts for each. So ways of representing text sequences in a way that can be computed on.
So we're usually transferring some type of representation that might include like probabilities of tags, like what type of evidence leads you to tag something as a, or classify something as a particular a class, right? Then we're trying to transfer that knowledge into a new domain where those labels may be preserved or adapted in some way.
go ahead.
Yeah.
Okay, so coming to now pre-training, the question the prof asked, are we learning anything? What are the kind of tasks we can use for pre-training? So you have a bunch of text and you want to learn some kind of representations on them, which is called as pre-training. And you learn those representations and you adapt those representations on the target task. So some examples of pre-training tasks we have already said, like count based, which is glove. I mean, a mixture of count based and prediction based, which is glove. Word to vec, which is based on prediction. We are not going to cover all of this. Elmo and BERT. This is some kind of pre-training that we do on text. And once you learn these representations, you can adapt them to some downstream tasks like name entity recognition or Q&A and so on. So there are two kinds of pre-training. One is supervised, where you use some kind of supervised task. For example, natural language inference. Even before Elmo and BERT, it was believed that natural language inference was a good task for learning universal representations. I think you can search for a paper on this. It's called as universal sentence representations. And you have unsupervised tasks like language models. I hope everyone knows what language model is. If not, we'll just cover the basics of it later. And if anybody knows what an autoencoder is, then you can tell everyone others what an autoencoder is. So these are unsupervised, where either you have where you don't need any annotated data, or you have annotated data within the text itself, like we do in language models.
Sorry, another question. How would you be using autoencoders in NLP, for example? Is there any task that off the top of your head maybe? Because usually, I don't know, I've used it for time series analysis, anomaly detection, but for NLP, how would
You can use a sequence to sequence autoencoder, where you are reconstructing the same sentence and hope that the representations that you learn from the sequence to sequence is good enough for your downstream tasks. That's one way of using it.
It's also for representation learning.
Yeah, it's one use for. I think even variational autoencoder is something which is famous for NLP, where you learn representations, and in the representation space, by just moving through the representation space, you can form sentences or infinite words. I think Cara can tell you that. Yeah.
How would that, for example, compare to embeddings from BERT or fast text Elmo in general?
Sorry, how is it different from?
Yeah.
How does it compare?
How does it compare?
Yeah, like maybe in terms of performance, or I don't know, like differences, like how well does it work in any task?
I think that's a broad question to ask. For which task?
Maybe the first question answering data set, for
Uh,
example.
yeah, earlier they used to use all these word to vec and graph. Now they use BERT and Elmo and so on. But I haven't seen any variational autoencoder
I
representations.
don't think there's any like broad collection of like embeddings that are made from autoencoded anything. Like there's nothing
Yeah.
out there, I think.
Right. Yeah. Yeah. It's not. There's nothing like, oh, we will use this architecture and this auto. I don't remember. There might be.
Not that I've seen as well. That's why I'm just curious.
Yeah, but I think yeah.
I'm not sure, but perhaps one reason why you would use autoencoders would be for dimension reduction. Yeah. So yeah, if there's too many dimensions, you can pass it through it and encode it to speed it down. I mean, to encode it in a representation that you might not otherwise have been able to done at such a low representation. I mean, I guess it's just an intuitive proposition. I think like the reason why these are options.
Yeah. So let's go ahead.
Yeah.
Okay. So yeah, very quick introduction to what contextualized word vectors are. So all these Elmo and BERT are called as contextualized word vectors, and we'll see why. One is word vectors, the normal word vectors, where you have a set of symbols in NLP, but you would want to represent it as continuous representations. So that's why you use word vectors. This was really famous. Like everybody started using these, where you have one representation for every word. There are various methods to get these representations. Will not go through it, but just remember these are symbols which are mapped to some kind of a continuous vector. So these are word vectors. Similarly, we have sentence or document vectors, where you would want a semantic representation for a sentence or for a document or a group of sentences. So you have one such representation, and learning how to learn them. Maybe you compose them from word vectors, or you can do or you predict the next sentence or the previous sentence. There are multiple ways to do it, but every sentence will have some kind of a representation. The hope is that this representation will help you do a lot of tasks in NLP. So that's the hope for all of these representations. And then comes contextual word vectors. This takes another approach where you say the meaning of the word depends upon the context in which it is used. So here you have a sentence called "We have two cats." So cats should have a different representation in this sentence compared to the representation in the next sentence. It says it's raining cats and dogs. Here, cats is used in a different sense, and in the first sentence it's used in a different sense. So the philosophy is you have a sentence and you have a word. The word's meaning should depend upon its context. So that's why it's called as contextual word vectors. And as you can already see, maybe one other famous example that we give in this context is the word banks. So maybe you have a fisherman on the rivers of the bank, or you can say the banks reduce their interest rate this month. Banks are used in two different contexts, and they should have two different meanings. If they do, does it help in the in doing better in the downstream tasks? So yeah, so this is contextual word vectors. And how do we learn them is the concept of Elmo, BERT, and other transforms. Anything to anything to discuss here? Yeah.
Go ahead.
Some examples for like sentence or document vectors. I think it's like like, is there any like downstream tasks that actually use like sentence or document vectors?
Sentence vector?
Yeah, that one. Because I know
So-
what vectors, right? It's like it's used a lot of times, and then contextual vectors also. Like,
Yeah.
But I haven't actually seen like example for the sentence or document vectors that is like, for example, trained on like source task and then like actually used in like higher tasks.
Oh, you can look at infercent.
First.
Infercent, INFERCENT. That's one, and then there's paragraph to vec as well.
Yeah, thought vectors are also.
Yeah.
I mean, they're widely thought of as sentence vectors.
Yeah, fast text.
Yeah.
Some things which are not called Cove, which is used for machine translation. So these are sentence vectors. But ultimately, even Elmo and BERT can be regarded as sentence representations. Yeah.
So the idea behind a sentence vector is that you just collect a series of words, and it's important that it's in sequence order, right? And that you find some way of taking all of the component word vectors and encoding them into another vector of the same dimension. So for example, you could just take all the vectors and average them together, but of course that loses positional information, right? John kissed Jane and Jane kissed John have two different meanings, so, unless they're both mutually happy with that. Then you need to understand that the ordering of the words matters, right? Okay, so most of the methods for doing sentence vectors keep some type of positional information there, right? Either relative position, like word A comes before word B, or some type of absolute position, right? Like this is I is the first word of the sentence, computer is the last word of the sentence, or something like that. Okay. Of course, there's a lot of problems with sentence vectors because if you try to compress a lot of information into a single vector, right? You may lose some fidelity, right? And typically how that is, you use some type of sequential encoder, right? You encode the entire sentence using an LSTM or some type of RNN structure, which is what we're going to talk about soon anyways. But that favors, let's say, information towards the end, right? So a lot of people have used bidirectional approaches to compute a sentence vector, right? So if you have a sentence vector, then it's very easy to say, well, could I make a paragraph vector? Could I make a chapter vector? Could I make a book vector? Could I make all humanities information into a single vector? And you could, I mean, it's just, averaging or something like that. But then, of course, you're using some fidelity of information that way, right? You can go the opposite direction too, right? Which is what subword embeddings are for, right? You have character embeddings. You say individual characters like A, Z, or something like that have an embedding, right? Or a subsequence of characters, which is what fast text is like, right? And you can say, I'm going to build up the representation of the word by doing the same thing as what people do with document or sentence vectors with component characters to build up a word, right? So you can say, as soon as you say A is made out of component B's, right? Then you can apply some type of encoding structure to do that, right? So you can think about all of those types of things, like a quarter is made out of weeks. So if I have financial information, I can encode it that way. Anything that has time series aspect, which language does, you could do that, right? A video is made out of frames, right? So the big jump here is that into contextual vectors, right? So contextual vectors mean you have the same data item, but it lives in different contexts. It's surrounded by different neighbors in the time series, so it has a different meaning.
I think we have to go faster.
Sorry.
Okay. I think for one, so we'll talk about pre-training now, and then one thing that one task which is used for pre-training is language modeling. So just a very one sentence introduction to language modeling is it takes in a sequence of words, and then it will tell you how likely is the sequence. For example, if I say this is a sentence, it's a perfect valid sequence of words. But if you jumble up that sentence in a nonsensical way, then the language model should say that it's not so likely in this language. So that's the basis for language modeling. It's useful for automatic speech recognition and machine translation. Maybe when you're translating sentences using machines, you have some alternatives to choose from. Then you would want to choose a sentence which is more likely to be an English sentence or a French sentence. So this is how language modeling can be used. So Elmo is the first contextualized word vector that we'll be talking today. What it does is it trains such a language model on a using a bidirectional LSTM, using huge amounts of text. So and then it has two directions of LSTMs. One is the forward and one is the backward. There are some character embeddings and word embeddings here. And finally, it has a softmax layer, which will say, okay, what is the next? It will predict the next word in the sentence.
Maybe you can point with the mouse.
Yeah. So you have softmax, and then it predicts the next word. So this is a basic language model with 2 directions of LSTM. It will concatenate it, concat the 2 representations. So you train this language model. This is the pre-training. You achieve the best possible result that you can with such language models. And now you would want to use it on some downstream tasks, like maybe say natural language inference. You take these representations and then you linearly combine the representations from these layers and then fine tune it on your task, maybe natural language inference and so on. So this is Elmo. So do you have any questions on this? Like what?
Actually, doesn't freeze I thought they freeze
They freeze, but they the linear combination is learned. Yeah, sure. This is feature based, like BERT talks about. So if you see the BERT paper, you have 2.2 is fine tuning approaches, 2.1 is feature based approaches. Feature based approaches freeze all the parameters in the pre-trained model. Fine tuning approaches fine tune all the parameters in the pre-trained model. Yeah.
So for the softmax probabilities, like does the weight updates of later make use of all the softmax probabilities or only uses the top one, like, for example, the ground?
Oh yeah, no, just
it
yeah.
takes into account more information if you use all the softmax probabilities. It's only the top.
So
It
this
just uses the top, right?
no, here in Elmo it takes, so this is one layer, this is second layer. So you have representations coming out of here, right? And representations coming out of here. It uses both of these separately.
But like, does it tune the representations
No.
using all the softmax probabilities, only the top prediction?
During fine tuning or pre-training?
Pre-training.
During pre-training, it changes everything. It's learning a good model for the language. Yeah.
I mean, what I meant was for the updates of the representations. Does it use information of all the softmax probabilities or only the top one? Yeah.
Oh,
I mean, I'm just trying to think of ways you can build upon or extend this.
So this one, the softmax, it just gives you the probabilities across the entire vocabulary.
Yeah.
Right? So you have to predict brown in this particular step, but it will check against the top probability that you have predicted. Yeah, the loss is the language modeling loss, which is the cross entropy loss.
Because it just occurred to me, like maybe an idea for extending or improving upon this is if we can also take into account the other softmax probabilities when we do the updates of the representations.
During pre-training.
Then there's less information loss that way, because maybe the second topmost softmax probability also has a lot of information we can mine.
Right.
Yeah. But I mean, that's a random idea of the top.
I think that's done more during inference where you don't throw away all the probabilities. Maybe if you want to next generate, right, you would want to consider other alternatives. I think you can look at the beam search, which is usually used for generation, where you consider like top 5 probabilities from here, but not during training. Yeah, and then there are other, I mean, yeah, I know what you're saying.
Yeah.
I mean, that, yeah. But not during training. It's not done during training, but maybe you can do it.
I'm not sure why.
Because during training, you're looking at like ground truth, and
Yeah.
ground truth only has like one thing that's 100%
True.
that thing happened. Whereas
Yeah.
like your second most probable thing didn't actually happen in real life, so you can't say like, oh, this is the second most probable thing because you don't know that it happened.
But
Yeah.
somewhere else in your corpus, you might have the second highest one appearing.
Yeah, but then in that case, it would be a separate training like example.
Separate
And for
example.
that example, that would be 100%.
Yeah.
So you should predict 100% for that
I
one.
see.
Yeah.
I see.
But you would require it more during generation. Or you made a mistake by picking the top one. I should have picked the second one instead. Then you can
Then
reduce
that's
some kind of errors. Yeah, that's being kind of. Yeah.
And it's related to the idea of label smoothing, right? Where you're taking the actual right answer and allowing some of the probability mass to go to other things, right? So that you have an easier time learning, right? Otherwise, you get something like a big spike, which is the good thing.
So now coming to BERT, we will see how transformers are used for language modeling. What is a masked language model and what is next sentence prediction? Everybody knows what sequence models are, like LSTMs and RMS. Right. So okay. So these are very slow to process for obvious reasons. You'll have to use the information from the previous word and the next word to change the state and so on. So they cannot be easily parallelized, and they in I mean it becomes difficult to handle long range dependencies. What do we mean by this is you will have to remember something from way past to answer questions in the current time in sequence modeling. Ideally, theoretically they should do it. LSTM should do it, but it still becomes difficult for various reasons like gradient explosion, vanishing gradients, and so on. So say you have a sequence to sequence model for neural machine translation and you want to predict this word, but this word depends upon the word which comes in the first position in the source sentence. So it becomes difficult to model these long range dependencies. So sequence to sequence models have some kind of disadvantages like these. So some ways to alleviate this is to use attention. Some ways to ease this is using attention. A general concept of attention is was was introduced in machine translation, where you use some kind of a representation which you get from sequence to sequence models, and use this single representation to generate words in machine translation. But the burden on that single vector is too much. Like you should compact all the representation into a single vector, which usually doesn't happen. What attention does is it decides the new decoder state in machine translation by linearly combining the different encoder states. Is everyone still on board? Okay. So the linear combination weights. How do you linearly combine? Is dynamically decided. Which are the attention weights? Okay. So the attention weights, how do you calculate? You have something called as a query. In terms of machine translation, the query is the current decoder state. You want a new decoder state, which depends on encoder states. So this is the query. And then you calculate some kind of a similarity between the query and the encoder hidden states. So in this diagram, you have a new decoder state, but you want this decoder state to be good enough to depend upon all the encoder hidden states. So you calculate some kind of a similarity between this decoder state and all the encoder hidden states. How similar is this decoder hidden state to all these encoder hidden states? So that's what is the similarity calculation. Okay, and then you have a set of similarities for all the encoder hidden states, and then you pass it through a softmax, which converts the similarities to probabilities. So you have some kind of a probability over these encoder hidden states, and then you use these probabilities to linearly combine them. So this is the basic concept for attention. I know it's too fast if you haven't read attention before. So ask me questions.
So it's like you want to add like more importance to some states that are more similar.
Right. Yes. And this concept is important because this is query. The encoder, so you calculate some kind of relationship between the query, and this is called as the key. If you have read the BERT paper, so and then you get some kind of probabilities which are attention weights. You use these attention weights and multiply them by something called as the values. The values in this case is again the encoder hidden states, and you get the information out. So this is like a normal mechanism. Is it okay? Okay, cool. So after this, then to explain self-attention, how much time do we have?
I don't know, we just keep on going.
Okay.
We're gonna end at 3 for sure, in case our session ends at. So,
okay.
Cara, how long do you need to go through? 40 minutes.
We can be as long as far as short as you like.
Okay.
I can do maybe like 20 minutes.
Yeah, 20 to 40, okay.
Okay. Should I talk about self-attention or let's
Is everyone clear about first this idea of key and query values?
Where does the query come from?
In this case, in machine, it's a basic framework And then the query can come from anywhere, but in machine translation, it comes from the decoder, let's say. Or the query is how similar I am to other encoder instances. The question is, I see it as a question asked by the decoder. So it's like, oh, I'm just asking the question to all the encoders and I calculate the similarities. So that's where the query comes from. In self-attention, it comes from the current time step. It asks question to other time steps. We'll see in self-attention how it is. Yeah.
Question. See the word that you use the word query can come from
Sorry?
anywhere.
Sorry?
So you say query can come from anywhere.
Yeah, yeah.
And I've seen that before. Where
Yeah.
else can it come from other than decoder?
Like I told you, in self-attention, it can come from the current time step.
Yeah, other than
Self-attention.
Yeah, other than
Maybe it can come from image representations.
okay.
Some patch of an image, you have a query, I want to see how similar is it to some word that you have. Maybe the patch describes a cat or something, and then you want to see where you want to calculate attention values. I might be wrong.
Okay, so I think you can relate it to search engines. We also have a course on information retrieval. So whenever you type in a Google search query, that's a query, right? And the key values you wish to retrieve are documents on the web, right? So the reason why they use this vocabulary is to make it as general as possible, right? So all we're trying to say is that when you think about attention, you should place attention on documents that are similar to you. So you can think about this entire process of self-attention or attention in general as a way of deciding which things are most similar to you, right? So you want to attend to things that are similar to you. So that's what attention means, right? So like Abhinav was saying, right? You have a current query. It's like, what's happening right now? Okay, that's my query. And I want to retrieve what things in my past are useful for my understanding now. So you can think of it like you currently have an information need, like when you type into Google, and you want to find documents in your past, right? Maybe through desktop search or maybe through web search. Okay, so hopefully that makes a good understanding. So it's the reason why they call it that is just to connote more general things, right? And the key thing that other part of this is that because it's just a key value retrieval, you can parallelize it, unlike the case of sequential encoding.
Yeah, that's what self-attention does. Yeah, you don't have to depend upon the representations that you calculated before. You can calculate your own representations now.
So if you're on Slack, I put a link there. That Stack Exchange is really, really useful. So the scribes can put the link in later. Okay, go ahead.
Okay, so so there was one paper which is called a structured self-attentive sense embedding in 2017, which I think was for the first ones to include self-attention. So this, what it does is they want to calculate representation, semantic representation for the sentence based upon the words that you have. So how do you calculate? So in order to do this, you will have to calculate the other words, the relevance of other words in the sentences for the current word. For example, you want to say how relevant is this particular word for the sentence representation. So this is where self-attention comes from. And how do you do this? It gets a little bit technical, where you have some kind of an LSTM, okay, and then you have n words. So these words, W's are the words, and T goes from 1 to n, and you get some kind of a representation through the LSTM, and they use a bidirectional LSTM here. You concatenate those, and you have n representations for one for every word. So so you have n words, and this particular h belongs to, has a dimension of 2u. So this is a matrix which is n cross 2u. So this is the initial representation that you get from from the bidirectional LSTM, and then they want to calculate how relevant each of these words are for the sentence representation. So how do they do it? They calculate some kind of a similarity again with the hidden representations. So this WS1 has a dimension of dA cross 2u, which is dA is some hyperparameter that you can use, So this whole thing will have a dimension of dA cross n. So what does this actually mean is they're calculating, I can see it as some kind of a similarity score being calculated for n different words. So this is dA cross n, right? So you have some kind of a similarity calculated for all the n words, and you calculate dA such similarities. If I'm wrong, then just let me know. These are not there in the paper. It's just what I thought.
Okay, well, we will put up the link if it's not already there. I think Abhinav did circulate this paper on Slack.
Yeah.
Guys can take a look at that
Yeah.
paper.
So once this is done, then you wanna pick the best similarity for each of these n words. So this is what they do by multiplying another weight, and you convert these scores into probabilities, which says, okay, you have n kinds of similarities, n different attention weights for each of these words, and you can use this to again combine information from different parts of the sentence. So these are the attention weights in this case across every word, and you use these attention weights to calculate these sentence representations. The next step they say is, okay, you have calculated one kind of attention over these words, which might focus only on one part of the sentence. Maybe there is a sentence like the cat and the dog, and you want to get information from about cat and its relationship with the dog as well. So they say this attention that we calculated just now focuses only one part of the sentence. We want to calculate, we want to focus on different parts of the sentence, and for different parts, we are going to calculate different kinds of attention. And they calculate R such attentions by changing this into a matrix, where you calculate R into N, where R kinds of attentions are calculated over the sentence. Why this is important is because I think even transformers use these kind of things, the same concepts, to calculate self-attention. So there is an attention module, and there is a multiple head attention module. So why do they need the multiple head attention module is to focus on different parts of the sentence, so you can form a proper representation. Was this fast or is it okay? Just know that it calculates some kind of attention over the words within the sentence itself, and the query comes from the representations of the word here, and the keys are the other words in the sentence, and then you calculate the attention and combine them to get the sentence representation. Instead of just getting one single sentence representation, they get our different sentence representation. Why do they do that? Is because you have to focus on different parts of the sentence. Yeah.
This is unsupervised.
This is
The right word is self-supervised.
this one. This one is not self-supervised. I think it's supervised. Yeah. I think the last
This is
layers.
sentence embedding model, so I guess it would be unsupervised, but I'm not sure. We can go take.
You can just take a look. I don't think so.
Is the number of is there a constraint over the number of words in a sentence?
Yes.
How do we eliminate how do we overcome if we have so many tokens in a sentence?
Which is very hyperparameter based. BERT uses 512 tokens, but you can flip it. Yeah, depends upon your. Again, it's very how much memory do you have on your computer? Sure, you can use more. It's good to use more, but I don't think so. It derive any value from using more as well.
So like everything in
Yeah.
deep neural networks, the more dimensions, the higher fidelity your data, but then the higher your data requirements are. Right. Like I've said many times to our own research group, you can't believe the deep learning results because it really depends on the application scenario and the amount of data that you have. Your data scale will matter much more than your architecture in general.
Okay, so this is self-attention. So this is the transformer module. So this is attention is all you need. We saw that you cannot parallelize in sequence to sequence models, and then you have problems in actually remembering long-range dependencies or getting information from long-range dependencies. So what it does is it has some kind of an attention where Q is queries, K is keys, and V is values. I'm going to talk abstractly like the paper does. Then we are going to talk about what query keys and values are in different scenarios, right? So this queue, like the paper says, it's a bunch of queries. K is a bunch of keys and V is a bunch of values. So every query in Q is dk dimensional, and every key in the set of keys is dk dimensional as well. And then every value in these set of values is dv dimensional. And then, so how many keys are there in this bunch of keys or a bunch of queries is D model. Just talking in terms of the language of the paper itself. So there are D model keys, D model queries, and D model values. What it does is calculate self-attention in encoder. So you see a multiple attention head, right? It calculates self-attention over the words in that particular sentence. And just like self-attention paper does R values, here they do something similar, which is H. That's the multiple attention. They do H times the same thing. So this is the multiple attention head. Is this clear? And why do they multiply? And this is the similarity. You are calculating some kind of a similarity here, here, and they multiply by 1 by root of dk. Why do you multiply this by this value? It's there in the paper. Just asking the questions.
For those of you who scan the paper cursor, why did they take the square root of the dk? What's the purpose of normalizing by that factor?
Sorry, I didn't read the paper. May I know what is dk?
dk is just a d-dimensional vector. It's just annotated by the dimension for the key. Yeah. Maybe
So
say
12 dimensional
yeah.
keys, and you take the root of 512 and divide all of that by that. So I mean, it's sort of a small issue, right? I mean, you can see that this probably doesn't make a whole lot of difference because it's normalizing all of the values, right, that are coming out.
Yeah, we don't even know whether it makes a difference.
It does make a difference, but why does it make a difference?
Numerical stability. I don't know. Doesn't sound like it's gonna make a huge difference here.
Yeah, I think it has more to do with that, though, because like the larger vector sizes you get, then probably the more sparse data you get. So if you divide it through, you're getting values in a particular range that are easier to optimize. But if you guys have read the paper, maybe you guys are clear.
I think exactly is that. When the queries and the keys become too huge, then your dot products will become huge as well. Then your softmax, if you have seen the softmax, it's like this, and your softmax reaches the top values almost near 1. And if that happens, then your gradient is the gradient and on the curve at that particular region is flat, which is almost 0. Then you're not learning anything.
Did you catch all of Abhinav's explanation? Because I mean, those things all make sense to someone who has the background, but if you don't have the background, you're like, I'm completely lost. It's so far.
Maybe this is the question.
Yeah.
If that's the explanation, then could we have taken logarithm of it instead of square root?
Yeah, I don't think there's a particular reason. I mean, people in information retrieval will make up math all the time. They're not really justifying why they're doing it. They just do it.
Yeah.
Yeah, and so a logarithm would probably work just as well, right? You're just looking at a penalty that's disfavoring large values, right? So you have a very high dimensional vector, then you want to do more normalization, try to squash values into something else.
Softmax can reach 1, right? Then we'll be
Softmax cannot reach 1, right? It's
zero.
normalized, so it'll reach almost.
Almost. I mean, log, you'll have to think about all that. Then you'll have to.
Sorry, I don't really have background in NLP, but just curious, like, what is the develop size?
So DK is usually a dimension size for the vector. So the vector is like for glove could be 384 or 512. Or sometimes if you're Google, maybe 2K. But if you're a research group in NUS, maybe even 128. I don't know. Something small.
I think it's 64 in BERT.
64.
64.
Okay. So
Okay.
are we all clear about what's going on here? What is this actually computing? What's the V? And are we clear about what's going on in the parentheses there? What is it computing? Anyone want to say? Well, what's going on in the parentheses?
Let me try.
Yeah.
Within the parentheses itself, Q and K is just not product, so it's calculating like similarity. And the value is just the think of it as like a hidden states for the encoder. So it's like a formula for calculating attention, and there's so many different formulas to calculate it. This is just one of them.
Yeah, exactly.
Yeah.
So
this thing in the parentheses that the softmax is calculating is just some type of coefficient of importance, right? To multiply the vector V against, right? It is saying for a particular word in the context, how important is that word to this current query word, right?
Yeah, I didn't understand like very well the concepts of query and key and value.
Also,
But maybe
what
you can give like a
example?
an example.
I don't have it on the slides,
So
but
I can try to get one. So let's say you have the word bank, right, which is a polysemous word. It has two different meanings, right? And that's your query. And somewhere in your previous utterances in the sentence, you have the word, financial. Okay, so it's going to, we want that word to be very important for understanding the sense of this word bank, right? So that would be your B, okay? But we're trying to calculate this thing in the parentheses, okay? So I'm using the key of that particular word bank and looking at the word, the word financial and the word bank will be the key and the query. And because they're close in the embedding space, they would have a high similarity value. That means everything inside of the parentheses will have a high value. Okay, so we are going to assign a high coefficient, something closer to one after going through the softmax, to the vector that's represented by the word financial. Does that make sense? Sort of?
Yeah.
Okay. So again, when we're doing multi-head attention, why are we doing that? Because we want to make sure that we have several different possible interpretations for a word or for a sentence latent in the structure, so that somewhere else downstream I can update that, right? So even though I have the word bank right now and the word financial earlier, right now it seems that's the sense of the word, but maybe later I encounter, river, right? And so I want to still be able to preserve the fact that bank has not been completely determined as financial bank, for example, right? So the multi-heads allow us to do that, right? To say, okay, I'm not ontologically committing to this sense of the word.
We can go into more detail later about what exactly the attention heads are attending to in BERT, right?
yeah. So like Bob said, you have multiple heads of attention where you are projecting it into some lower dimensional space. Like it helps you focus on different sentences. If you want to go through the math, we can go through the math, or we can skip this. And we can go to see what BERT does and what are the things. Do you want to go through it? You can just say, it's fine. If you want to go through it. We have around like 10 more minutes for me.
How many more slides do you have? Like 50?
4, 5, 6, 7, around 27, but I mean not 27 more, but it's 9 more, yeah.
No, those for skipping. Okay.
Yeah.
And talk about BERT.
Yeah, I think we can talk about BERT. This is the basic unit. So this explains only the self multi-headed attention. Then there is addition and normalization which happens. So consider this some kind of a module, and they replicate this module 6 to 12 times, and this is a transformer module. Why does it? I think you can read the attention is all you need paper and figure out for yourself how you can parallelize this and why does it become parallelized, because now you are not calculating any, there's no LSTM, it's just attention everywhere. Self, here it's a self attention in the encoder, here this is the decoder, and this has a self attention in the decoder as well. And if you know machine translation models, then there is some kind of an attention like I showed you between the decoder and the encoder, and that also happens here. So there is an encoder decoder module which will help you in translation. BERT uses these modules and stacks them 6 times or 12 times, depending on whether it's BERT base or BERT large. Okay, so you are learning, so you use these transformer modules, which are attention based modules for learning representations in BERT. So BERT comes now, and you have a bunch of text. You want to learn some representation on this. So what it does is this is how BERT represents a particular input. So this is a sentence where my dog is cute, maybe this is and that's my language model. He likes playing, and he likes playing maybe. So what it does is it appends a CLS token at the beginning of the sentence, and if there are two sentences, then it sorry. So this is a separator token. So this is not a mask token. So this is a separator token which separates two sentences. So my dog is cute is one sentence, and he likes playing is another sentence, and you append a separator at the end of it. So why do they do this? Maybe we can discuss. I'm not sure. Which is usually done to indicate end of sentence, start of sentence in NLP, and they do this.
Which one?
The CLS and SCP. So which are the starting and the separator token for particular sentence, but they don't have CLS here. Strange.
The CLS at the start of the first sentence, if I'm not wrong,
Yeah.
is used for like classification.
Classification.
So it's like it's not just a token. It sort of like aggregates information about the entire sentence, about
Yeah.
both of the sentences that you are
Yeah.
representing.
Yeah.
I think so. It's different from SEP in that way.
Yeah.
Yeah, I think CLS
Yeah, I
stands
think
for
makes sense, yeah.
classification, which means that you're planning to use the downstream embedding for classification.
Yeah.
So if you want to do joint learning, you would prepend a different token at the front. It's
Yeah.
basically telling the embedding that you want to do a certain task with that. Exactly why that works, we can talk about more, because I'm also not that clear about why adding a token at the beginning seems to tell this whole system that we want to do classification now.
Yeah.
Is the outputs from the classification token used in the loss function for BERT when it's doing the pre-training?
Okay,
I think so.
I'll come to that. No, they're
No,
not
it's
masked,
not.
I think.
Okay, they're not masked. Yeah, they're not masked.
Yeah.
That's for sure. Otherwise, you wouldn't know what you're doing.
Yeah. They're not.
Yeah,
Not during pre-training, right? No, I don't think so.
Then really what's the purpose of?
Yeah.
So actually,
Or they should be masked, right? Because
the question answering, I think like for squad 2, if it's an unanswerable question, it gives you a CLS token instead of like the actual set.
right, he's asking during pre-training, are you learning some kind of a representation for CLS star?
No. I mean, for example, if when you are pre-training the BERT, the output from the classification token could be like 1, 0, 2, 3, or 4. Is this used to compute the loss parameter in the loss function?
Yeah, I think that you learn separate representation for this. Yeah. I think I read it somewhere. Yeah, I think you do. They don't mention that even sometimes I think they are masked. Yeah.
Also, they are also masked at the same time, so that's how they.
Yeah, they don't exclude it. At least they don't exclude it here. They learn. So if you see the differences between comparison of BERT and OpenAI GPT in the paper, they say they learn separate representations for these. BERT learns separate. BERT learns embeddings during pre-training for separate SEP, CLS, and sentences CMB. Yeah. I think there should be. Yeah, master. Yeah. Okay, let's go ahead. So we have the token embeddings, which are just they are they are representations which are learned on the go, and then you have separate embeddings for sentence A and sentence B, which are learned during pre-training as well. And then you have position embeddings. They start with some pre-trained positional embeddings. So what are position embeddings? Since we have only attentions, there is no sense of which position in the sentence a particular word comes from. So the attention is all you need. Paper uses something called as the positional encoding, which are based on sine and cosine functions. If it is in, so you can just look through the paper to find how they calculate the representation at that particular position. So this is what is used in BERT as well. So the main advantage of BERT comes from the kind of pre-training that they do. So they have two tasks that they jointly optimize. One is called as the masked language model. So in the masked language model, you have a sentence, and then 15% of the tokens in the sentence are replaced by the token mask. The task is to predict only those tokens which are masked. So this is the masked language model. So only those words are predicted. How is it different from denoising autoencoder? If anyone knows what denoising autoencoder is, you add some noise to the input and you want to reconstruct the input. This is a denoising autoencoder. How they are doing something which is very similar, right? They are corrupting the input, but they are predicting at those particular mask tokens. So how is it very different?
Yeah, so the question is, why is that a good idea? I mean, you're throwing away information in the training data.
Yeah.
Which is definitely useful to have. So why would anyone want to do that?
It's just like how BERT to vector is trained so that you can learn the representations around the surrounding words.
Yeah.
Something like that. Go on.
Not quite. I think it's a bit different than that. Yeah.
So why does it help? That's the
And
question.
then why does it help?
So both of these strategies, as Abhinav said, are ways to make the machine learning model generalize better.
Yeah.
It's a regularization.
It's a regularization strategy. So everyone knows what regularization is, right? Why does it regularize? Because when you mask out words, you're telling the model, I'm sorry, you just don't have access to this information. You need to predict based on your general knowledge, okay? Because otherwise it may fixate. You say, I always have this word here, and that word is the key reason why this is tagged this way, or this has this particular classification. So by shooting out random words, just like in dropout, dropout in neural models, right? It's doing the exact same thing. This is dropout for natural language. Okay.
So that is a regularization parameter, 15% is.
Yes, yeah. The more you drop out, the more general model you get, right? As you can see, if I remove more words, I have less things to predict, right? But then it's gonna be, less useful. The more you put in all the things, the more data you need, right? If you have more data, you take the dropout rate less, right? I mean, more. You would drop out more if you have more data, because you can depend on more things to fill in your gaps.
So now it has to predict a particular word just depending upon the context, because it doesn't have any information here. Or now when you see sat on, and then you want to predict something here, it can be cat or dog or whatever. Yeah. So this is one. And then the other advantage of BERT is so if there is a mask here, you can't just depend upon the words which come before. You'll also have to depend upon the words which come after, right? So BERT uses context from both sides. So this is one other advantage. And how do they do it using transformers is something which is there in the paper. They mask out tokens which come afterwards, and they mask out tokens which come before at different points in time, and then they calculate representations. Is it okay? Yeah. So this is one pre-training task. The other one is next sentence prediction, which is given two sentences like this, you will have to predict whether the second sentence follows the first one. Is it really the next sentence? Because then it will give you, when I talk two sentences and the second sentence doesn't have anything to do with the first sentence, then it's not so good, right? For natural language. If if the model has the ability to do this, then maybe it will do well on sentence tasks. For example, in LLM, natural language inference, where you say whether the second sentence is an entailment of the first sentence or a contradiction and so on. So they want to do this as well. So they include this in the pre-training. It's clear. Okay.
So actually the masking doesn't happen all the time, right?
Yeah. So comes next. Yeah. So the masking, they say they masks certain tokens of the particular sentence, but this happens only during pre-training. During fine-tuning, you can't mask. Right? It's a sentence from your test data set that you want to fine-tune on, or some other task B that you want to fine-tune on. There are no mask tokens. So this creates some kind of training and fine-tuning time discrepancy. So what they do is, so instead of always replacing tokens with mask, they 80% of the time they are replaced with mask. 10% of the time they are replaced with random words, and the other 10% they will just replace it with the same word. They are not changing anything. So every training instance, you pick 15% of the tokens, and 80% of the time you either replace it with mask, 10% you replace it with a random word from the vocabulary, or you don't do anything at all. You just read it. So this way it has all kinds of information during fine-tuning as well. It has learned representations for this particular word depending upon the context. So this is one thing. Yeah.
Do they do next sentence creation during fine-tuning?
Yeah. Fine-tuning?
Yeah.
No, fine-tuning is done in a different.
So there's no mask.
There is no
NSD
mask.
as well.
Sorry?
No mask. No next sentence creation.
No next sentence.
Just fine-tuning.
Yeah. Okay, this is about BERT. We're not talking about results. We are not talking about hyperparameters, how to fine-tune it on different tasks and so on. Those are easy to see from the paper. Quickly, I will go through ExcelNet. So this is, oops, I think something. Okay, forgive me for this. So some of the disadvantages from BERT. So this is not knowledge-based BERT. So this is some disadvantages are, as you saw, there are like there is training and fine-tuning discrepancy. But if you have two mask tokens within the same sentence, they are predicted independently. So the prediction of one token doesn't depend upon the token from the prediction of the other token. So this is not so good. Can give examples, but so and then there is something else called as the autoregressive language models, which just depend upon the previous context or on the forward context, and these are known as autoregressive language models. And BERT is something called as the autoencoder language model. ExcelNet is something which came after BERT. They produce something. They suggest an autoregressive language model to learn from bidirectional context. And how do they do it is by using tricks. Because autoregressive is something which you can learn only by using one directional context. But if you permute the tokens in a way such that the context which comes after also comes before, if you say you have tokens 1, 2, 3, 4, you permute it and make it 4, 3, 2, 1, and you want to learn a representation for the word 1. Now you have 4, 3, 2 before 1, so you can use that to calculate representations. Don't want to go through it, but yes, so there is variations of BERT, which is ExcelNet, and there is a new paper which is called as no BERT, which depends upon knowledge bases. So language models are not always factual. You want to make them factual. For example, if you are generating sentences from medical domain, maybe I can tell you, then you would want to be factual, and you want to depend on knowledge bases for this. How to include representations from knowledge bases for this is a new paper from ACL, I think. It's called as no BERT, and there are an ever-growing list of BERT family. There is distal BERT, which are smaller versions of BERT. Albert, I don't know what is that. Haven't had the time to read it. Camembert is definitely a dessert, but a French dessert, obviously, and it's
cheese.
it's cheese. Oh, sorry. It's cheese, and then even the title says it's a tasty model for French language modeling. Roberta is robust BERT. If you come up with something else, then you can add it to the list. I think Karen can take it. Yeah.
So like now that we
Switch slides over.
kind of know, we kind of like know what BERT does, kind of, but I just wanted to give like some examples of things that BERT is like learning, so we can have a less snappy picture of what's happening. Because when I first read the BERT paper, I got very confused.
Just like everyone else.
And still confused.
And so like I just wanted to like here are some words so we can understand what's happening. So I will talk first about attention because that's what we talked mostly about. But there's also a separate section on like what's happening in each layer of BERT because there are 12 layers. So attention. So this is paper by Clark et al. 2019 at ACL, and they looked at BERT, the BERT attention hits. So there are 12 layers of BERT base, and each layer has 12 attention hits. And basically, what they were trying to do is figure out what are each of these hits attending to. So first, why do you care about attention? It's because it's kind of easier to understand what an attention hit is doing. It's more interpretable than, let's say, just looking at this is a vector for 2. Like, what do all these numbers mean? What do all these numbers mean? Who knows? But if you look at this nice representation of what attention is, basically what's happening here is when you're trying to construct the representation for 2, what you're doing is looking at each of these words and you're saying, oh, which word should I care about? And in this case, you care a lot about store and you don't necessarily care as much about all these other things. So it tells us not just like what is happening in the representation, but how we're building this representation as well. So what they did basically is they took 1,000 segments of 128 token long Wikipedia data, and then they ran it through BERT, and then they took all the attention weights out, and they're trying to see what each of these things each of these hits was attending to. So interestingly, what they found was that some attention hits attend to positional offsets. So for instance, hit in layer 3, hit number 1, attends to the next token. So you always have found ones to look for in and in ones to look for Taiwan, and so you're just looking at the next token. Whereas something like hit 111, which is in the first layer, it's looking very broadly at all of the other tokens in the input. So 9 of the attention hits put more than 50% of the attention weight on the previous or next token, so like this. Whereas some of them are just like, oh yeah, let's look at everything. Interestingly, this is mostly in the first layer of the network where you're just kind of like getting your bearings. And this basically has the effect of aggregating a bag of vectors representation because you're just saying all of these words are relevant in some way. We'll just concatenate them all and put them all into my representation. But interestingly, the CLS token in the last layer also attends very broadly, which kind of fits in with the idea that because it's looking at next sentence, whether it's valid or not, right? So it wants to look at the entire sentence and say, given what we have so far, let me try and encode everything into my CLS token. And they also found that hits in layers 5 to 10, so further higher level layers, attend to the SEP token a lot. And they sort of suggest that this is not for any particular reason, but that the SEP token functions as a no-op layer, as a no-op attention. So when you look at the gradient offsets later on in the layers, if you attend to SEP, there's very little gradient change. So you can see looking at SEP or attending to SEP as sort of saying, forget it, I don't really want to attend to anything else. I'll just like don't do anything with this attention hit. So the next thing that they tried to do was to see whether BERT attention resembles dependency parsing. So what kind of information are we attending to? Is it related to the syntax of the sentence itself? So what they did was they took the most attended to word, and then they decided that word was a dependency relation, and then they compared it to the Stanford dependency parser outputs. the dependency tree. And then they found that in this case, no one head captures the dependency syntax overall. So if which kind of makes sense, right? So no single head is saying like, oh yes, I will always point to every single dependency relation, which, because that doesn't make sense. But specific heads seem to specialize in capturing particular kinds of dependency relations. So for instance, this is head 9.6, which points prepositions to their objects. So this is off and relates to bonds, and then you have in, which relates to trading, and to, which relates to active. This is quite interesting. It's quite cool because what you can do here is long distance dependency relation. So this is at which response, which the dependency relation is to auction, which is actually quite far away. It's a number of tokens away, and it allows you to do these long distance dependency relations reasonably well as compared to, let's say, an LSTM, where these gradients might get lost. So what else? I don't know. It's okay.
Do you want to stop the presentation and then reload it? Maybe it's not there because did you put it in recently? You can just hit reload and see what it does.
Sure. I think I had another picture. Yeah.
These heads, the analysis is done on all the heads in all the layers.
Yeah. So 144 hits. Yeah.
Yeah, so those of you in the group, you know that analysis is a big part of what you need to do, right? So don't shirk your duty when you hear other people doing 104 analysis of attention heads. I mean, that's just like a mindless, fruitless task. But you know, the whole point is like you look at this and you say, okay, it's actually doing something very interesting because like you already heard, attention is looking at everything all the time, right? So the fact that it's still recovering useful information, like trying to find dependencies, or even next word. Next word is not an obvious thing that you would expect a model to come up with, right?
It's coming out the LSTM again.
It's basically saying that the next word is important for things, which of course we know, but you're asking it to recover that from having no information at all. Or you're just giving a bag of words and you're saying, okay, well, figure out what words relate to each other, right? And then the system says, well, you know, actually the order in which you pick the words out of this basket of words actually matters, right? So that's pretty interesting. And at the beginning, you can see it's doing the same type of things as you do in computer vision, right? So if you know the vision architecture of ImageNet or other things like that, right? Convolutional neural networks, you've heard of all that, right? They say that layers like 1 through 3 give you basic textures like corner detectors, circle detectors, etc. And these things get composed gradually as you go up the pipeline. You can see the same thing happening up here, right? This is doing the same thing. Like the fact that the next word is important, sort of like a basic feature that you would want to provide. It's doing, as Abhinav said, the work of an LSTM, which is to say the next word is important. Yay. Okay, but it's sort of obvious, but it's not completely non-obvious to this model, right? Because this model is you just gave it nothing, right? You just gave it nothing, and then it's trying to figure it out. So you know, at the beginning they're trying to attend to everything because they don't know, and then gradually these relationships are getting cemented down.
I was gonna show an example of something else. There we go. So one other head is very cool. It does co-reference resolution. So this is head 5.4, with 65.1% accuracy, it links co-reference mentions to the head of the antecedent. So for instance, she here gets linked to her. So like these two things are related, and it can also link like it can do fuzzy matches. So talks and negotiations here has some sort of dependency relation, which is quite cool because BERT is not trained on any of these things. But yet it somehow manages to capture some of these relations with some degree of accuracy. And this is compared, so the benchmark here was some sort of, so the benchmark here was, you look at, let's say, maybe two tokens before you, two tokens after you. They look for the kind of relationship that gave the most accuracy, and then they compare this actual relation that you get with that benchmark. So these are some cool things that BERT attention hits can do, but they also note in the paper that a lot of the hits don't seem to have any particular thing that we can sort of infer out of them. So for a lot of the other relations, dependency relations, the improvement over that baseline is very small. You can't really tell exactly what each of these attention hits is doing. Yeah. Let me now talk about what happens in each of these layers. So like there are 12 layers of BERT, right? And you start with just words and you end with some sort of representation. But the interesting thing is that somewhere in between, it's able to learn all of these interesting syntactic details and what details about the words themselves. So there was this paper by Jawhar et al. At ACL, and they asked the question like, what are each of these layers of BERT doing? So which parts of BERT are looking at syntactically correlated parts of speech, or syntactic or semantic features? Which parts can do subject-verb agreement, and that sort of thing. And I'll just talk about maybe two things. So the first thing is phrasal syntax. What they did was they took representations of each kind of phrase. So let's say a noun phrase is he, and they took the representation from each of these layers, the outputs from each of these layers, and they just like did dimension. They plotted it on using T-SNE. And it's very interesting because things that have the same part of speech kind of look similar in the first layer. So in the first layer, all of these like adverb phrases will look the same. Noun phrases will look the same. Prepositional phrases have similar representations in the first few layers. Whereas if you go to higher layers, then the part of speech representations are no longer in that layer. So you can't really differentiate something that's a prepositional phrase from a noun phrase anymore in the higher layers. So it seems like the first few layers are the layers that are doing part of speech recognition and stuff like that. And then they also looked at they were trying to probe each of these layers to see what kind of information each of these layers was embedding. And the idea here is like, you take the output of each layer and you run it through a classifier that can give you a prediction for, let's say, how long is the sentence, or what is the tense of the verb in this sentence. And the idea here is that if the simple classifier works, it could indicate that the layer itself has some sort of representation of that information. Does that make sense? So that layer of the model is capturing the feature and is therefore passing it into the system. And so the prediction works well. So there are three kinds of features that are discussed by Kono et al. Basically, they're split into sort of surface features, syntactic features, and then semantic features. Like coordination inversion is what happens when, for instance, you have like I ate a sandwich but I'm still hungry, and you flip it around and the sentence becomes I'm still hungry but I ate a sandwich. And the question here is, can you tell whether a sentence has been flipped or not? So that's a very deep sort of question, as opposed to how long is a sentence, which is quite a surface query. So they ran all of these layers through all of these tasks, and they found that the layers with highest accuracy on the surface things were the first few layers. The layers with highest accuracy on the syntactic features were the middle layers, and the layers with the highest accuracy on the semantic features was the last half of the layers, basically. So it sort of seems like BERT is splitting up these tasks into different layers so that each layer does something different. And it's kind of similar to vision in the sense that you're doing like smaller things in the first few layers, and then you're aggregating this information to get more complex information in later layers. Yep, that's pretty cool. Does anyone have any questions?
One question.
Yep.
What paper is this?
This paper is it's on the slide. I put it on the reading list.
Oh, okay, thank you.
There's also a video where he talks about this, and I just clipped the slides from there, so you can also watch it. it's very cool. If there are no questions, I'll talk about one final thing, which is long distance syntactic relations, which is a task where you're trying to do subject verb agreement. So basically you're trying to decide, in this case, whether you're going to put is or are here. And this task seems simple if you have a simple sentence, but the task gets a lot harder when there are intervening nouns with opposite numbers. So for instance, in this sentence, you want length to have single agreement, but you have this thing here that's plural. And then you have something like this with one, two, three attractors, which may confuse the system, but you actually want it to be singular, which is. And so the system has to sort of be able to learn these long distance dependencies reasonably well. And again, they found that the middle layers capture this syntactic information quite well, which is similar to the thing that they did previously, right? But what was interesting is that as attractors increase, performance drops, which makes sense. But the later layers are better at doing things that the previous layers aren't good at. So when you have 3 or 4 attractors, the 9th layer has higher accuracy than the 8th layer, which is what's getting the right answers on a lower number of attractors. So it's interesting that you require deeper layers when you have long distance dependencies as opposed to short distance dependencies, which can use a lower layer. Yeah. So I hope this gave you like an insight into what BERT is doing under the hood. That's not just math. It's like put some meaning into the math. Yeah. Any questions?
I hope there are questions, especially from those of you online or those of you in the room who haven't spoken.
Yeah, so it uses self-attention, right? So because self-attention, according to the formula, like it kind of find the similarity between like the query and the key. So I kind of expect like you expect it to put like the most weight to like the word itself. So if you go like several slides, I think one of the very few slides that show, yeah, this one. So I kind of expect like 2 to have like the most weight because it's like the same word. So it's called self-attention, right? And then it calculates the similarity between the query, which is 2, and all the key below, right? Yeah. So I'm just wondering like, why is this not always the case?
Why is 2 not attending to itself?
Yeah, like I kind of expect it to have like the most weight because it's like the most similar word.
Usually, in the self-attention, you can see that there's a transformation matrix. So it's WQ and WK. Yeah. So when you're using self-attention, basically your 2 is act as a key, and there's another 2 that acts as a query. So when you project into different latent space, they may have different representation. So it's not necessary that each self-attention would have a highest attention.
And it's not syntactic. I mean, why would you expect it to have?
I mean, it's the same sentence, right? So like same word representation, at least at the
But,
very beginning.
Yeah, but the representation, like we said, can have different functions. And here the function is to attend to the argument of the proposition.
So for instance, in this case, the function of this representation is attend to the next thing. And then that will change the representation, right? And so then in the next, let's say the next layer, it might be, oh, attend to, we now know you are a preposition, attend to the object of that this preposition corresponds to, maybe. Yeah.
I want to ask if there's any works that try to regularize heads and attention heads to make sure that they focus on different parts, because some attention heads might focus on the same functions, and if we just add more heads, then it doesn't diversify the functionality of the head.
I have no idea, but that seems like something that someone should be doing.
Yeah, I think there are a lot of inefficiencies in the math that people are doing. And it's clear that there's a lot more that you could do to refine the model. Right? So
Yeah.
I think that approach would work quite well if we could work on that type of model.
Remember seeing one paper,
So it done
people
again.
do attention on top of the head as well. So they argue that some heads isn't important, others are more important, so they put it out to the
They
layers.
attend to the heads.
Yeah.
Nice. Meta attention.
Yeah, I mean, you have 12 attention heads, so somehow that information is getting compressed down to a single argument already, right? So that is something that is being done implicitly, but you're saying it's explicitly in the model to do that as well.
Yeah, I mean, you can, so when they talked about how the heads in the higher layers don't really attend to separate, they basically said like, these heads aren't really doing anything anymore. So a lot of these heads just are there, but they're not adding anything to the way the representation is calculated anymore. Yeah.
So I think it'd be interesting to look at, when you train it for a particular task, whether certain heads make more difference than others. Like when you have several different attention heads, you're basically saying you have some information that could be helpful for a downstream task, right? And so it's optimizing for that. So for example, if you have just like a coordination inversion task inside of the things that you're trying to apply it to, then the fine tuning should produce some attention heads that are helpful for that, right? But having that task as one of the component tasks that you can do will just generally get you better at doing language tasks in general, right? So this is, I guess, the whole point of doing joint tasks or joint training is like you train it on many, many different tasks. All the tasks are, I guess, fine-tuning some attention model somewhere to say, okay, this particular information in the sentence is important for that particular task for this particular word, right? And then you're storing that somewhere in the attention head. And then when you look at a new task, if it actually, that piece of information is correlated to that task, it becomes important, right? So we know some tasks, it matters what gender objects are. Some tasks, it matters what the, co-reference is. Some tasks, it may matter whether there's an agreement or not between certain parts. So all that is being calculated, right? And then potentially through the attention heads being saved so it can be used in the downstream task. Okay, when we come to graph encoding, which is, I think, is it next week? I don't remember. Yeah, this will be related because, I mean, when we do graph encoding, it's almost the same idea, right? The whole idea of graph convolutional networks is that one thing is not well represented by itself. It's represented by the neighbors in the graph, right? And so we're doing that here, except the neighbors are everything in the sentence, right? So you can think of that connection between, transformers and graph convolutional networks, right? This is very.
I think indeed, stay we are in graph neural networks, the graph attention networks also make use of the concept of attention.
Yeah, so this idea quite naturally transfers over, right? And I mean, and part of the reason why it works so well is just because it's parallelizable, right? We can just get it almost for free. I mean, temperature outside, aside from the problem, you can get it for free. Okay, so it is 2:59. Let us thank our presenters, Abhinav and Cara, for a very okay. And so if you haven't signed up already, please do sign up your slot. Okay, we need you to do that so that we can help you predict your workload. Okay, and also make sure that this reading group remains useful to all the attendees, especially the ones in our group. So thanks very much. Those of you online, thanks for joining. We hope we can figure out a better participation model from you guys because it doesn't work very well, I think, quite yet. Okay. All right. Thank you.
The decoder attention. The decoder attention.
Just have the idea about explaining the square and continuous. I think it has something to do with the chi-square distribution. Square is the sum of the square of standard solutions.
Yeah.
With the project of K, I guess it's reasonable to exercise each element.